In this tutorial, I am going to show 19 different ways to handle missing values. I'll cover what are the different types of missing values using simple broadband data to explain, and later I'll be using Titanic and Atoll census data with Python code. I'll share what the specific method is about, when to use the method, and sample code using Python libraries. Now, let's first take a look what are the different types of missing data. Missing completely at random, MCAR or MCAR. Missing at random, MAR or MAR. Missing not at random, MNAR or MNAR. So these MCAR, MAR, MNAR are acronyms used in statistics to describe different missing data mechanisms. They are used to classify the reasons why data point might be missing in a dataset. If data is MCAR, it can be handled relatively simply using technique like list-wise deletion or imputation. But if data is MAR or MNAR, more sophisticated methods are needed to avoid biased results. Now let's take a look at missing completely at random. In this case, if we get a data set where there are observable data and partly missing data, so the relationship for the missingness, in this case, it doesn't depend on complete observable data or partly missing value. Let's take an example. So here I am showing an example with mobile broadband data. So if you see, these two variables are observable. So which is like this one, which we represent with X. And download speed is where the missing variable is there. This is Y. Now you can see from this data, the missing value is because data limit is fully utilized. And here there is no relationship between missingness and observed or missing variable. So that's why you see in missingness, there is no relationship between these two, which is green and yellow. Now there is always some factor, which is missingness, not related to X or Y. We don't know based on data. So that relationship will be there for all three types of it. Now let's look at the second category, which is missing at random. We call it MAR. So in this case, we will see the missingness has a relationship with observable variable. So it depends on observed data, but there is no relationship between missing variable. So again, with the previous example, if we have another column, say data limit usage, we can see when data limit use reach 100%, the missingness has happened in download speed. So missing value depends on another observed variable. Now the third category, missing not at random, MNAR, we'll see that the relationship with missingness has both observed variable as well as missing variable. And we are not particularly sure what has caused that missingness. And that's why it's called missing not at random. Again, the previous example, if we have data limit usage, here we can see missing download speed is available for 80% or 75%. So we can say the download speed missing value has relation to download speed, data limit usage, and some other unknown variable. But we can never be very sure what has caused this missing. We know that it's missing beyond 75%, but we cannot predict the value. So that's why it's missing not at random. Now, the simplest way of handling missing data is discarding data. We'll be covering two methods. One is called list-wise deletion, complete case analysis. The other is called dropping feature or variable. It's also called available case analysis. Now, list-wise complete case analysis, let's go back to our example of mobile data. Here you can see mobile package, download speed, data limit. There are many missing values for all this. So what we can do, we can remove these corresponding rows. So we can delete them. So after deletion, data would look like this. This is the most common approach for missing data, to omit the cases with missing values and just use the remaining values. If the data is missing completely at random, it can be used. When the proportion of missing data is small, then it can be used. But we have to remember that there are few drawbacks for this method. We may lose information since this delete dataset size can reduce. And if the missingness is due to MNAR or MUR, list-wise deletion can introduce bias into analysis. Now let's take a quick look at code. I'll be using Titanic dataset for showing missing values imputation related to numeric fields. We'll be loading libraries pandas, numpy, sklearn impute, simple impute, canon imputer. We'll also import MSNO library, which will show us missing data in a very nice graphical way. Matplotlib is required for showing those graphs. And then from feature engine, we'll be importing random sample imputer. Now first step, we'll be loading Titanic dataset. We'll just create a copy to use the data because some of the steps after imputation, data values will change. So we just want to retain a copy for later usage. So first we run the Titanic.info and we can see age has some missing values and cabin has some missing values. So let's run df.isNA and sum all the missing values. We can see there are 177 missing values for age and 687 for cabin. Similarly, for embarked, there are 2 missing values. Now, as we have seen in exploratory data analysis, it's also important to understand what is the percentage of these missing values. So we'll run again to find the percentage, and we can see age has 19%, almost 20%, and cabin has 77%. Now, next thing we can do is visually how this entire dataset looks like. So we'll be using MSNO matrix. This shows for age there are missing values, and for cabin a lot of missing values are there. So this is a very nice way of showing missing values. Another way to show drawing a bar using the same MSNO library, and here also we can see that for age 714, and while for cabin it's like 204 values are only available. We can also run a heat map to show only those missing values, and we can see some correlation but not much. If you see, there is no strong correlation between them. The values are between 0.1 to minus 0.1. Now first let's look at list-wise deletion or complete case analysis. In this case we'll use the drop NA to drop all the rows with missing values. So after that we can see if we run the dot shape, there are only 183 rows remaining. Rest all got deleted. And visually, if we again run the MSNO matrix, we can see all missing values are basically deleted. Dropping features or variables. Here we can see for download speed, there are a lot of missing values. So what we can do, we can delete this feature or the variable itself. Now, this is usually used when there are very high percentage of missing values, or the feature determined is irrelevant for target variable. In some cases where feature engineering is done, the dropping feature might be required. Now the drawbacks for this one is dropping feature may again lead to loss of valuable information. If we drop the feature selectively based on missing pattern, it can introduce bias. Dropping feature might reduce the model's ability to generalize to new data. Now let's take a look at code. Dropping features or variable, available case analysis. Do a drop in A, but in this case, we are using just a subset for age and embark. We are not taking the entire dataset, but only these 2 columns. And you can see after this deletion, we have 712 rows still available. Next, we'll be going through imputation of data. There are various ways we can impute data. We can impute data using mean, median, mode. We can use last observation carry forward. We can use next observation carried forward, linear interpolation, common point imputation, adding a category to capture missing value, frequent category imputation, arbitrary value imputation, adding a variable to capture missing values, random sampling imputation, multiple imputation. We can also use some sophisticated predictive or statistical model-based imputation like linear regression, random forest, k-nearest neighbor expectation maximization. Now let's go through each of them one by one. Mean imputation. So in this case, we'll be taking mean of this variable and replace this field. Like in this case, mean for this variable is 130. So we are replacing this with this value. Similarly, for median case, we'll be taking the median value and replace it. In this case, median is 155. So we are replacing with this median value. Now, when to use mean or median? When data is missing completely at random, we can use this. When the variable is normally distributed, usually we can use mean. If it is a skewed data, we can use median. And both these methods are useful for continuous variables. Now, a few drawbacks. This imputation reduces variability and can lead to biased estimates. May not work well if large portion of data is missing. So let's take a look at the code. Next, we'll take a look at mean, median, mode imputation. Again, we'll copy and use the simple imputer from sklearn. And our strategy, or in this case, we are using the mean. We are applying it on age variable. Similarly, again, for median and using on the age variable. Now, if we run this against the entire Titanic dataset, and since we have created two new imputed fields, one is called age mean impute, and another is age median impute. These are the age variables which are not a number, means these are all missing. And after imputation, the mean was 29.699118. So all these missing values are imputed with these values. And median was 28. Mode imputation. This is more useful for categorical variable. For illustration purpose, here you can see for download speed, the most frequent value is 200. So that's the value we are replacing for the missing fields. As I said, it's used for categorical variable. When mode represents common plausible category, then it's a very suitable way to handle missing data. It can lead to over-representation of the most frequent category. Let's take a quick look at the code. The next we'll be doing mode, and for that we'll be using pandas mode feature. We have to be very careful while doing this that we don't include all the missing values while taking the mode. Otherwise, it may be the missing value which is the mode in certain cases. In case of age, it's like 20% are missing. There is very likely it may be the age which is the mode value for that particular variable. So we'll first remove all the missing values for age, and then we'll take the mode, and the value will be taken from this way. Here its mode value is 24, and if you see, all these missing values are replaced by mode 24. Next is last observed carried forward. Download speed. We have missing values in these three records. Now what we can do, we can carry forward the last observation. So in this case, 90 will move to this field. Similarly, 155 will be carried to this and this. Next observation carried backward, NOCB. So in this case, we can see download speed. There are a few missing values, and values will be propagated backward. So if you see 155 moved here and 180 moved to both these records. Now, when to use this? It's inappropriate for non-time series, not suitable for data without a meaningful time order. NOCF can be used in time series data where missing values are likely to be like the most recent known value. NOCB can be used in time series data where future values are more relevant for imputation. So both LOCF and NOCB is predominantly used in time series data. It's not suitable for non-time series data. A single unusual value can propagate through multiple imputations, which means its sensitivity is immense for outlier. It can create artificial pattern in data, especially in very long sequence of missing values. Now let's take a quick look at code for last observation carry forward, LOCF, and next observation carried backward, NOCB. This actually we can use the pandas fill in a method, and there is something called ffill, forward fill. This we can use for LOCF, and there is another method called bfill that we'll be using for NOCB. So again, let's take a look after imputation, this newly created imputed fields, age FF and age BF, how it looks like. To explain it in a better way, what I have done is, since all these are the missing record ID, I've taken the previous or next record for each of them to explain it. If you take the previous and next records, in this case, you see age, fourth record has 35, fifth record has none. So in age forward fill case, 35 is moving to this fifth record. And for backward fill case, since the next record was 54, so 54 was propagated to fifth record, which is previous record. So this is how all these values are forward fill, and these are like backward fill. Linear interpolation. Again, this is usually used in time series data. So let's explain using the same example of mobile speed data. So here there are two missing values. How it is calculated is this value is a linear interpolation between this fourth and sixth record. So we calculate using min and impute this value since it's a linear interpolation. Similarly, for this one, it's coming from 150 plus 160, which is 310, and divided by 2, 150, which is like a midpoint, is a linear replacement. This is useful for time series data when we have evenly spaced time series data and we believe the missing values follow a roughly linear trend between known points. It's useful for continuous variable. If we believe there is a gradual change in the variable, then this is a suitable method. In this case, we are assuming the variable change gradually over time and there is no abrupt change in variable values. Now, in terms of drawbacks, it assumes a linear relationship between neighboring values. Linear interpolation can introduce bias into data and it may not capture complex patterns. Let's take a look at code linear interpolation. In linear interpolation, we'll use the pandas built-in interpolate, and method that we'll be using is linear. Created a new feature, linear interpol, and again taking the subset of those missing values and before, previous, and next values. And if you see, this fifth record is taken as a mean from this and this, 35 plus 54 divided by 2, which is 44.5, and that's how it is imputed. Similarly, if you take the 19th record, which is 31 plus 35 divided by 2, which is 33. Common point imputation. It is similar to mean value, but more suitable for ordinal values. For a rating scale, using the middle point of most commonly chosen value. For example, if we rate the speed as a rating between 1 to 5, if there are two missing values, we can use speed rating the most common value or the midpoint, say either 3 or 4, as the replacement value for these missing values. So here we have used 3 as the replacement. This is similar to mode, but mostly used in ordinal values, and its drawback is also similar to mode imputation. Code is similar to mode imputation, so I'm not going to show separately this code. Adding a category to capture missing value. In this case, there are missing values here for mobile package. And what we can do is we can add a new category as missing to show these data points are missing. This is perhaps the most widely used method for missing data imputation for categorical variable. All the missing observations are grouped in the newly created level. It does not assume anything on the missingness of the value. We'll be using adult census data for all categorical variable imputation demonstration. Now, in terms of usage, the missing values are not simply random occurrences, but rather indicate a specific characteristic or condition. In those scenarios, this is suitable. If many values are missing, creating a separate category can help to preserve the information contained in the missing data. So these are the two scenarios we usually use this method. Now, in terms of drawbacks, it increases dimensionality, as one extra dimension or categorical variable potentially increase model complexity. It can complicate model interpretability. It may create class imbalance if the missing category is rare. Let's take a look at code now. Let's take a quick look at UCI machine learning dataset portal, from where we'll be using the dataset to demonstrate this imputation method. We'll be using adult census data to show imputation for categorical variable. Feature engine is one library that we'll be using. From UCI portal, we'll be load the dataset. Once dataset is loaded, we'll take a look at how many variables have missing data, and using MSNO matrix, we can see there are missing data in work class, occupation, and native country. These are the three fields where data are missing. We can also see using MSNO heat map that there is a strong correlation between occupation and work class missing data. Again, if you use the MSNO bar, we can see these three has missing values. Here, we are going to take a look at adding a category to capture missing values. So in this case, for occupation data, what we're trying to do is filling all the missing values with a new category called unknown. So this is how we are capturing it. Now, if we take a look after we have imputed this value with the unknown, what is overall category in occupation field? And you can see unknown has come here. And also, if you see, the occupation now has all the values available, and we don't see anything in occupation in terms of missing values after this imputation. Frequent category imputation. In this case, we replace the missing value by most frequent category. So here, if you see, for mobile package, most frequent category is first plus. So for these missing values, we'll be replacing with first plus. Usage is mainly for categorical variables, and drawbacks are almost similar to mode imputation. Code is also similar to mode imputation, thus not showing here separately. There is another very popular method which is called arbitrary value imputation. In this case, we can find an arbitrary value which may be -1 or 999 or something to show that this is a missing value. So in numeric case, we can use say -1 or 999 to show the data is missing for this specific value. So when to use this? When you want to distinguish missing value with a specific marker, say -1, 999 or missing, you can use it. For variables where specific value can represent missingness. If missingness is not occurring naturally, we can use this. Drawback wise, this can distort the distribution and may affect model performance. Here we'll be using same UCI data to demonstrate arbitrary value imputation. In this imputation method, we'll be filling all the missing value by an arbitrary value. Here we are using missing. We are using the pandas fill NA method to fill the missing values, and also created a new variable called occupation arbitrary. So after this, if we take a look, we haven't updated the occupation, so there are values still missing here, but occupation arbitrary, all the values are present. The same thing we can see visually, occupation arbitrary don't have anything, while occupation still have missing values. Next, we are going to go through adding a variable to capture missing value. In this case, what we do, we create another additional variable. This method is also known as missing indicator method or flag method. Basically, what we are trying to do is we are flagging or indicating this value is missing. So wherever there is a missing, we are putting it as 1, and if not missing, it's 0. So this variable is binary. It takes only value 0 or 1. Typically, mean or median imputation is done to original variable where this value is missing to capture those observations where data was missing. So in this case, we are using 200 as a mode value to replace in the download speed. When to use this? When missingness itself is an information, we can use this. For variables with significant amount of missing data, this is useful. When missing data is not at random, this can be useful. Drawbacks, it increases model complexity and potentially it lead to overfitting. Splitting the information between original and indicator variable can reduce statistical power. It can also make interpretation of the original variable's effect more difficult. Here we are going to take a look at code for adding a variable to capture missing values. So first we are again copying the census data in the data frame data, and then we are creating a new variable called occupation missing. And in this case, for all those missing value, we are making it an integer, so it will show 1 if it is missing and 0 if some value is present in occupation field. Let's first take a look at what is the most common value in occupation. So you can see the occupation, the professional specialty is the mode value in occupation. We have done the imputation by replacing this mode value in the occupation field, and at the same time occupation missing fields we can take a count. And if you see, there are 30718 as marked as 0 and 1843 are imputed, or those values where it is 1. It's coming from this line of code. Now let's take a look at a few sample where the occupation field is imputed. So here see, occupation field is imputed with the most frequent value, which is professional specialty, and all these corresponding fields are marked at 1 in occupation missing newly created variable. Random sampling imputation. Random sampling imputation is a simple technique used to handle missing data. It involves randomly selecting values from the observed data point to fill the missing value. So in our example, we'll be taking data in that missing variable field, existing data, and randomly select to impute. When to use? When you want to maintain the original distribution of the variable, you can use it. Effective for small amounts of missing data. Again, this introduces randomness and may affect reproducibility, because every time we run, it will impute randomly. Let's look at code sample for this method. Next is random sampling imputation. We are using here the random sample imputer from feature learn, applying it on variable age, and after transformation you can see it's randomly assigning value. This is also called hot deck. So these values are randomly assigned from all the available values in the age field. Multiple imputation, mice. So multiple imputation is a statistical technique that involves creating multiple complete datasets by filling in missing values with plausible variable. Multiple datasets are created and then analyzed individually. Estimates are combined to obtain a set of parameter estimates, and finally pooled result is used as an imputation value. As a flexible way of handling more than one missing multiple imputation, there is a popular method called MICE, which is multiple imputation by chained equations, which is quite popular, and it comes under one of the advanced strategy for imputation. When to use? When missingness occurs in multiple variables and follows no simple pattern. This is useful for both MAR and MCAR. It can be computationally very expensive, and it may be even more difficult computationally if the dataset is large. Complexity. The method is more complex to implement and explain compared to other simpler imputation technique. Result can be sensitive to the choice of imputation model and number of imputations. Let's take a look at code. Multiple imputation. Here we are using iterative imputer, which is multivariate imputation by chained equation. So once we use the iterative imputer, and if you take a look at age and newly created age mice, this is how the value looks like. Now we'll take a look at advanced imputation method using predictive and statistical model based imputation. We'll go through code on linear regression, random forest, k-nearest neighbor, and expectation maximization. In terms of their usage, since these are complex method, it's only used when we know there is complex relationship between variables in our dataset, and normal imputation may not capture the essence of this relationship. This may be also useful when you have sufficient data to train accurate predictive models. This can be also used for mixed variable types when dealing with both continuous and categorical variables. In terms of drawbacks, these methods are more complex to implement and interpret compared to simple techniques. Computational intensity, all this requires more computational power, especially it becomes challenging for large dataset. The imputation models may overfit to the observed data for small sample sizes. The quality of imputation heavily depends on the choice of model and the accuracy of the predictive model. Let's go through code sample for all these 4 methods. Linear imputation. So we'll be importing a linear model, linear regression from sklearn. Our X data variables are P class, sibling, and P arch, and target variable is age. So first we are removing all the features where age is not missing, and target also where age is not missing. If you print it, it will look like that this is the shape after removal of data. After that, we will be doing a linear regression. We'll fit the model. You will train the model using the X train and Y train. So this is X train, this is Y train. Once this is done, then for all the missing values, we'll be just using the prediction, and then we'll apply those to this variable. And basically we are creating a new variable, age_lr. And if you see, we are applying the predictions in age_lr field only. We are keeping the age field as it is for later comparison purpose. Here we have updated 177 values. Next we'll do random forest imputation. Again the same way, 3 fields or 3 features we'll be using as X data and age as a Y data. Similarly, we'll be handling all the non-null fields for training purpose. Reset the index, and we'll use the random forest regressor from sklearn. This way we train the model using those X data and Y data. After that, we'll be applying the predictions, and then similarly we have created variable called age random forest, and we'll later take a look. It looks like the imputed values. Similarly for KNN, we have used the KNN imputer and ran the transformation using the age field. For maximum likelihood and EM, we use the iterative imputer, and again applied the iterative imputer on age field. Now we'll only take the columns which are starting with age, because these are the columns we have created: mice, linear regression, random forest, KNN, and MLEM. And again, I'm taking the before and next values for all these NaN records, and then we can see how the values are calculated based on all these different methods. Now, I want to bind all these concepts together, and I want to call them AI Sutra. So this is first AI Sutra that I want to share with you all. Sutra is a thread. So here I'm calling this sutra the thread that gives you an idea how missing data handling should be done for your specific challenge. There are 6 techniques that we can implement to impute missing values. The simplest methods are like mean, median, mode, and arbitrary value imputation. You can use one of them based on your situation. Next method is based on time series or sequential data. For these cases, we can use last observation carry forward LOCF, next observation carried backward NOCB, or linear imputation. When we are dealing with categorical data, we can use adding a category to capture missing value, or frequent category imputation. If dataset has information missingness, we can use a variable to capture missing value, or you can use common point imputation. If dataset is complex and there is missingness in multivariable scenario, we can use statistical method like random forest, linear regression, random sampling imputation, multiple imputation or mice, or you can use expectation maximization or k-nearest neighbor. If high proportion of data missing in the dataset, recommended approach is either use list-wise deletion, which is complete case analysis, CCA, or you can use dropping feature or variable, which is available case analysis or ACA. So with that, we have come to an end of this lesson. Thank you so much.